Hello? Hello?
Hello, can you hear me?
Yes.
Uh, I think I will just wait for Dr. Lee first.
Okay.
I just set up my software as well. Okay, I think I can start now. I'll just share screen first. And 1 second. Yeah. Can you see the screen or?
Yes.
Okay. So of course, we tried to run all of the different simulations, the corner simulations. As you can see, we had the PSRR, CMRR. Also, some of the simulations we needed to do were the DC and the stability and transient. Of course, we ran all of these. So if I, for example, if I open one of them, for example, the PSRR, if I open the schematic, you can see we created a symbol for our design, and also we have an enable so that nothing is floating, right? Everything is connected. And as you said from our last meeting, we have to connect it in PSRR negative feedback, right? So if I go check the symbol from inside, 1 second, it's not. I open it from somewhere else. 1 second. I just opened this one for now. So you see, this is the current source, the band gap, the tail, and you see here is the enable. So we connected the enable something like this, like a gate switch. And anyways, the main problem we have is that when we run the simulation, we get something that looks like this. Wait, I show you. Something that looks like this. We get like a negative decibel. So this is, for example, this is for the CMRR. So the CMRR simulation, we get a negative when in the specs, it should be from positive 65 to 100. Same thing can be said about the transient and everything else. So, for example, transient, we also get negative values. And the reason this doesn't really make sense is when we run this, for example. Wait, I show you when we run this in a different schematic. What we did was we have connected the VN minus and the VN plus. You can see here we connected them where VDD over 2, and here also VDD over 2, but the VN plus has a voltage differential. So that, and the differential voltage, we just sweep it. So you will get a graph that looks like this. This output voltage you can see is around positive 14, positive 10, sorry, positive 10. The second stage output is around positive 10, positive 11. So if we have a positive voltage output here, why is it that we get a negative decibel in the corner simulations? This is one thing I don't really get, because all of our simulations in the corner are pretty far out, I would say. So is it fine if you can maybe give us an explanation briefing about how this corner simulations work, at least?
Can you go back to your primary?
Yes. Yeah, this one is for transient. This is the transient one. Oh, regarding the transient, when we run, you see it says error. If we remove the VCM plus 0.01, if we remove these, it's not gonna give us an error anymore. So I also don't know why when we remove VCM, the error goes away. This is also one problem we faced.
It actually VCM plus 0.01 is when, because the input step is like 0 V sub VDD divided by 2 plus 10 millivolt step up. So if your output can track the inputs, so that it the output side, it also have the VCM plus 0.01, so it can show the values. Yeah, maybe that's the later we see the waveform. And the CMRR, why it is negative, is, in my understanding, is because the we want to eliminate the common mode noise. So that's why if in negative when you're using the 20 power of 10 power of minus some numbers divided by 10 divided by 20, you will get 0. You will get, how to say that, 0.0 something, so means that the common mode noise can be reduced. And what other things?
All right. Regarding the common mode noise, I would assume the main problem can lie between the differential MOSFET here, right?
Differential?
I mean, the differential, not, I would say these two MOSFETs, the M3 and the M0. These two, I would say, if we maybe modify the width of these two MOSFETs, it could maybe fix the problem with the like you said, the common mode error thing. Is it?
I will check. I will check first.
Because actually, we try to change the whole circuit. Nothing changes much actually. Maybe like we changed these, the PMOS, and also the differential pair MOSFETs. We also decreased. We decreased the band gap current. So the current flowing from the band gap, we decreased it, and we didn't really see much change as well. So I'm not really sure. Maybe the problem is with the transmission gate, but from my own experience, I've always used this combination, and I believe it doesn't really bring that much difference to our circuit. So I don't think maybe the problem is with the enable signal. Maybe it's more towards the, I would say maybe if we modify the two differential MOSFETs, it could help, but sadly, like it doesn't really do much. So we're kind of, I would say, stuck.
You mean?
Yeah,
The
we're
problem
stuck
first
at like the
is
negative. Yeah, we're stuck at the negative decibel. We can't really go above the negative.
CMRR should be negative, right? Because we don't want to amplify the
CMRR should be because in the specs it shows positive. So
I
I'm
think
not
this
sure.
is just how to say magnitude, absolute values.
Magnitude.
Magnitude.
Okay.
Because if this one is positive, your common mode noise will affect your everything. So I think that should be negative. And I think my test bench got like, I put a minus in front, so you can tabulate your data in positive values.
Oh. Let me see. I think, okay, but wait, actually, let me go back to the pictures we took. I think I have it somewhere. Wait. Yeah, this is also a PSRR. I would say, okay, regarding the PSRR, because this is the one we started with and we did most of our simulation with, right? You see it's at negative 60. It doesn't exceed the negative 60, right? So if we say that this is in magnitude, PSRR, the minimum is 65. Is it still acceptable like that, or
try to push it further
further
until
down?
minimum 65? Yes.
If we push it further down, you said the maximum is 100, right? 100
Yes.
decibel, but here it exceeds also 100. So isn't
you can see the test bench there. We measure the PSRR at 1 hertz. So you you just see 1 hertz only. You just measure the
Oh.
so
So is here, right? This
yes,
is until here we check, right?
yeah.
Okay, okay.
The high frequency region we don't no don't have to consider.
Okay, I see. All right. So it's only here, right? Okay.
Yes.
Same thing with the CMRR
Yes, measure at 1 hertz.
at 1 hertz. Oh, okay. Hmm. And it's fine that it's negative, right? It's just a magnitude thing.
Yes.
Oh, okay, okay.
And I saw your phase margin, the dot plot in the image just now. But
Which this one?
yeah.
This is
This
the
one, yeah,
stability.
this cannot start from negative
Oh,
because
okay.
open loop gain should be as a positive.
Uh,
We can check it later.
I see. Okay. Oh, before we go into like the stability, I just have a few more questions regarding PSRR and the other one as well. So, CMRR, um, if we want to like, if we want to modify it for the CMRR, sorry, if we want to modify it, then shouldn't the thing that changes the most are these two MOSFETs?
Yes.
These two should like do the most modification for, right? And
Mm. This one I need to check. Check. I later.
oh, okay,
I will give back the answer to you later.
okay, okay. Maybe one more. What else?
And I see your CMR actually, that I mean that is too high. Exceed the spec, is it?
Yeah, this one is negative 100. So the spec is around 60, 65 as well. So it should be
Actually,
here.
yeah. Ideally it is larger the better lah. Okay, I will check. I will confirm the things first.
Okay, so you're saying maybe like if it's large, because actually they're saying the maximum is 100.
100.
So
Yes.
why not they accept above 100? Is it like will it affect the actual chip in the future or?
I don't think so, but let me confirm with Mr. Yadi first. Then
All right.
okay.
Okay, no problem. Um, is it the same also for the PSRR? If it's above 100 also is a good thing
Mm,
or for PSRR, the lower the better?
mm, the higher the better in negative.
Okay, I see. So I
Oh,
think we
oh,
just try to.
sorry, I interrupt a while. Just now the value in the spec sheet is positive value, right? But now here is negative. Actually, can you clarify on this? Actually, the value should be negative or positive.
Mm, Actually should be negative, but I think in the spreadsheet, the spec is magnitude. We it's just magnitude.
Magnitude.
But in reality there should be negative because we don't want to amplify the noise, common mode noise and the power supply noise, right?
Oh,
Okay.
I see.
But usually rejection ratio, the noise is in the denominator, right?
Yes, V out divided by VDD. Yes.
Yeah, then wouldn't it be the higher the better? V out is compared to noise, if the noise gets smaller, then of course your dB will get larger and larger, right?
Yes. Wait.
Then if we look at negative 60 dB here lah, if we do a brief calculation, it's about how many times 60 dB is it 10 to the power 3 times? This
Yes,
means that
1000.
the V out is a lot lesser than the noise.
Yes.
Right, but right, it should be positive dB, right? If we want the thing to perform normally.
Let's say VDD
Because
noise is 1 millivolt and output is even smaller, 100 milli, 10 milli, 20 log.
20 log V out over V noise, right?
Yes.
Then
So
negative is 1000 times smaller.
yes. So means that the power supply noise doesn't affect the V out. The change in the power supply doesn't affect the output.
Oh, so the dB you mean here is how much does the V out change correspond to 1 millivolt difference? Oh,
Yes.
okay. Oh, I see. Oh, so it's the calculation the other way around. Okay.
Yeah.
Okay, I think, yeah, I have one more question actually. Last time you said we check from 1 hertz. So I just want to know this frequency is based on the sound frequency or which type? Because in this simulation it calculates from 0 to 10 gigahertz. So why that much change if we're only gonna check only this side, only for 1 hertz?
Actually, sound spectrum is 20 hertz to 20 kilohertz.
Oh yeah.
Yeah, but
Oh.
I checked. I confirmed with Mr. Eddie before. He said we measured at 1 hertz, and
As like the
this
minimum frequency
PSRR,
needed?
yeah, this PSRR is a power supply, so we inject the noise to the power supply from the frequency of the noise from 0.1 to 10 gigahertz. So
Yeah.
that means that when the frequency of the noise increases, the power supply able to reject more noise if we see from this PSR AC plot. Yeah. Something like that. This is just to see the PSR across versus the frequency of the noise. See how the circuit perform in power supply rejection, noise rejection. Yeah.
Okay. So I just need to tweak it a bit so it's around more than 65.
Yes.
All right. I think we try to do that. Okay. Okay, I think if we don't have questions regarding the two PSRR, CMRR, one main problem we're facing is the transient. So you saw the transient last time. Sorry, this stability. Let me try and open the transient first. Yeah, this one. So the main issue right now is we can't actually run the simulation because it will just give error continuously because of this thing. So I can just remove the VCM plus 0.01 on this SR small step and the large step. If I remove these, it will work fine. But when it actually like shows the graph, everything is just turned off. I would say it's just a constant value. So I'm not really
Can
sure.
you run the simulation?
Okay.
Don't remove this. Don't remove. You run
Okay.
first. Let's try.
Okay.
You mean there is no
Nothing actually.
waveform? No
Just
waveform come out. Is it? I think there should be waveform. Just the values is not showing here.
I see. Let's actually check. I don't remember because last time I remember it just gives.
How about the other team? Have you managed to fix the error issue? Is it the console still shows the netlist remove? Okay, this one you need to bring out on your side as well. I think you share the screen later on.
Yeah, you see, it's all error, so can't really do much here. It only shows the number down though. Oh, wait, sorry. Okay.
Can you ungroup?
Ungroup. Yes. Well. Yes, here.
See your V out is negative value.
V out. Yeah, it's negative. I'm not sure why it's negative though.
This op-amp operation region should be positive, right? V sub VDD divided by 2.
Yeah. If you check here, the operating region here, you can see it's actually in the positive when we run it. It's
Can you
like positive
go
10.
back to a transient schematic?
Let me go back. This is transient? No. Never mind. I just open it from here. Yeah.
Looks okay. Can you go to primary?
What is it? Wait. Yeah.
Go to waveform. Yeah, your V out is not following input because in negative feedback configuration, V out should track input, right?
Yeah.
How about your DC plot? Can you open DC?
Haven't checked DC. I'll try it now actually. Let's see. DC. I open the schematic first and it should be like this, correct?
Yes.
I just try to run it first and see. Could it be that maybe I connected the pins from the both gates? Could it be that the issue?
Mm. Do you put we see later.
Sorry?
We can see later we check the schematic.
Okay, okay.
Yeah, you see the V out minimum is negative. This
Yeah.
should not happen.
Yeah.
DC ungroup. Yeah. V out should follow VIP,
Oh,
but you see your V out.
it's not following it. Yeah, it's
Yeah.
stable, like not moving.
Yeah, so I think your op-amp might not function.
But why is it not functioning now? Actually, because previous
Can you
test.
go can you go to prime wave?
Yeah.
DC prime wave and go to results on the toolbar and then annotate advanced. Can you scroll to corner 21? Corner
Yeah.
21 is typical. You just click OK. And you tick DC voltage and DC OP values and DC voltage. And then OK. Enter.
Enter.
Enter the schematic. Enter the symbol. Your op-amp. Yeah.
It's a cutoff.
Yeah.
Why is that?
When enable is high, can I see your enable?
Yeah.
Before this is when you don't include enable, it does the circuit work.
We use the enable, and I think it should work without the enable. Yeah. But we haven't really. I don't really know how it's reacting now with the enable on. Not sure.
Enable high.
Maybe it's.
Can you zoom in?
Sorry, wait. Should be here is like high, and here is low. This side. So why, when here is high, it's off?
Okay.
Is it the body is connected wrong? Is it? Do you see the body? the body of the NMOS, this one.
That is, that should go to ground. Yeah.
So this one is fine, right? It's fine like that.
No. Can you full zoom? Oh yeah, fine. It's okay.
Yeah.
And this, can you go to the bias side?
The which one?
The band gap side.
Oh. I'm not sure.
The PMOS source should be on the top right.
Sorry?
For the output of the band gap,
Yeah.
the PMOS, the source should be on the top right.
Yeah, should be.
But it seems like this. Is it too? Yeah, the source is pointing downwards.
The PMOS?
Yeah, you see the source terminal.
Wait, this one you
Yeah,
mean? This is
yeah.
pointing here to this here.
Yes, source should be to the power rail.
Directly, right? Okay.
Okay.
So you mean I just connected like this?
It's
Do you know why
okay.
it's read only? Because I cannot edit.
Why you instantiate this symbol?
Sorry?
Where you instantiate this symbol?
Here. It's this one.
Yeah, the schematic is locked. I think someone is opening this schematic now, so that's why.
Hmm.
Yeah, it's okay. We go back to the schematic first.
So I just connect this directly here, right? The VDD.
I don't know. No, is
Because here it's connected after the switch.
it is also VDD, right? This is
This is
this is
just
also your VDD.
Yeah, it's VDD, but it's like after the enable signal. So if the enable is off, it cuts off connection from the op amp and also the band gap. So I also connected here. If I connect this band gap directly to the VDD, it will still be working even when the enable is off.
Okay.
So I'm not sure if it will do much change or not.
Can you go to the tail mirror current? Yeah, this one.
Yeah.
Yes. Full zoom. Press F. the current mirror, the lot, the PMOS current mirror lot of the op-amp. Can you zoom in? That not this one.
This one?
Yeah. Can you press left key?
Left key?
Yeah, you press. Yeah, okay. 5.0. Later you try to remove the enable, see if the circuit works.
Okay, I can
Because
try.
this current mirror, and after the enable, your VDD now is 7.1 volt. It
Yeah,
should be
it's
9 volt.
so much voltage drop, right?
Yeah, it should be 9. Later you try to remove this enable.
Maybe I
See
can put a buffer here.
new inverter.
No, I mean a buffer. After the switch, I can try maybe a buffer. So if the enable is on, there will be voltage drop. Then the buffer will pull it back up to VDD.
Okay.
Can try this one.
Yeah, you can try it. And make sure, yeah, the input, the current mirrors and the input transistors are in saturation. Make sure.
Okay, I'll try to add the buffer and see. If it still doesn't work, then I can try to remove the enable fully, and I'll check.
Yeah.
Okay.
Ensure the functionality first.
Yeah. Okay. So the transient simulation, just to make sure, how do you want it to? It just copies exactly, or should it amplify? For example, okay, the DC. You're saying that the V input is increasing, right?
Yes.
So the output should increase by how much? Should it increase by double, or it should
No,
amplify?
it will follow exact same.
Exactly the same.
Yeah. You can use search. Go to Google search. Negative feedback. Open. Look. It's okay. They don't show up waveform. Can you add on a waveform?
But just copies, is it?
Yeah.
Oh. Okay.
So this one got amplifier. Can you remove everything and detect unity gain?
This
Yeah.
one?
Yeah. You scroll up. This one, is it?
This one.
Yeah, something like this.
Okay, I see. Well, we check the transient also should have the same results.
Yeah, it will follow VIP.
Okay. Okay. I think I'm done with my part. If my teammates or anyone wants to take over.
By the way, Mohan, I think I see one. You go back to a schematic a while. I think I see something. Maybe you need to confirm with Daniel as well, lah. If you zoom into your current log for the op-amp, the first stage. Yeah, first stage. Yeah. The PMOS on the second PMOS there, the body should tie to VDD as well, right?
Yes. Oh yeah, right.
This one?
Yeah.
I don't notice that one. This one should go to VDD, the highest potential.
Highest potential.
Supply
Okay.
voltage.
Oh, yeah. So you mean like VDD from here?
Yeah.
Or from here? After when we have the enable?
It should, from here. You need to ensure this is very close to 9 volt, let's say. If VDD A is 9, after enable, this should be 9, around 9.
Yeah, okay. If we put a buffer here and it's 9, then it's also okay to put it here as well.
Yes.
All right. Okay, I'll try that as well. Yeah.
And the output PMOS also.
Output PMOS. This one, yeah.
Yeah.
This one.
Yeah, this one.
Oh, okay. All right. Yeah.
Mohana, your enable pin, how much voltage does this apply to the gate, to the transmission gate? Yeah, this one. Or also 9.
This one is 9, yeah. But the voltage drop is 7.
This NMOS VGS contributes the voltage drop 1 point. Yeah.
Maybe on time try to adjust a bit, maybe make the width as large as possible. Let's see whether it can up.
Because right now it's 20. I'll try to increase it.
Maybe can we have the other group first? Then because the other group also they cannot even run the simulation. Yeah, maybe we have the other group to show what happened to their design.
Yeah, I'll stop sharing my screen now.
Okay, so back to you, Stephen.
Can I see the waveform? I think I faced this issue before. Okay, let's see the waveform. where is the V out plot? Go back to V out impossible area. Can you try to close custom compiler everything and then reopen again? I think I faced this issue before. You close custom compiler everything. Yeah. Sometime might be the software error. Mm, yeah, open again. Yeah. Can you go to your schematic? Oh, yeah, the test bench schematic. Schematic. Yeah. Oh, yeah. You don't label the output net V out. Can you press the wire? This wire. And you type full capital V out. Yeah, it cannot. Yeah, yeah, go to prime wave. Prime wave. Yeah, yeah. also is also negative value. Not working.
Stephen, can you show the console? Because we see from the console, it says that one of the netlists there, a few netlists they are ignoring, or you see there's no signal for the current.
I off. Can you go to the symbol? Schematic. Oh, because now this instance name is I10. In the prime wave is I0. Yes, I0. Can you change to I? You press the symbol. Symbol. The green box. Yeah, you change from I0. Prime wave.
Try to run again.
Yeah. Yeah, I think you need to check the functionality of your, because you can see the V out is negative value.
Can I see your schematic as well? Because maybe your PMOS, you put it also to the VDD and see if it changes.
Yeah, Stephen, do the same as what Mohanad did just now. Open the schematic and then try to look at the corner 21, see whether the DC operating points of all the MOSFET are correct or not.
Not seeing. Can go to prime wave. Prime wave. Prime wave.
The
Just
simulation
now,
test bench.
where you run the simulation. Yeah. The results. Yeah. Yes. Oh, okay. Take yeah, OP values and node voltage. Yeah. I think better we go to DC. I think DC. DC. Yeah. Yeah. Right. Because this is time zero. Your another impulse is like -10, so hard to see. Um, Later you can save this Testbench so that you don't have to set up every time. Yeah. You run simulation one time. Untick is okay. Later it's okay. Go first. You can see there's a MN41 at output. Um, later I show. Yeah. Later I show how to get the tabulated format from there. Yeah, V out -10, -11. Yeah. You click the DC. Yeah, ungroup. Yeah, is negative value. Okay. Go to primer. Yeah. We see the operation region results. And okay. Advanced. Yes. Yes. Okay. You tick. And the most region also tick everything. Okay. Enter. Yeah. The bias working. Can you zoom in your op amp? Yeah, here. Yeah, you need to check again. Maybe because the tail current not mirror correctly. Can you see the size? NMOS, yeah, NMOS tail. Yeah, this one. Mm. Yeah. Yeah, you try to make the transistors operate in saturation after this. See,
What does the blue circle stand for?
blue circle is sub-threshold region.
Threshold or sub-threshold?
Yes.
I think more or less near to cut off already, right? Just like the other team.
Yeah. Yeah. Not not able to achieve the VD shape. Really, yeah. Yeah, we can check again later. I think every transistors based on the current mirror load input transistors. Let's go back to primary. You click there's a click to add, right? Where your cursor pointing just now, go down. Move your cursor down. Yeah, here. Down.
Last row, click to add.
Last row. Yeah. Sorry. You go to the column right next to it. Yeah. You go to calculator. Yeah. Right. Left side. Yeah, this one. At the analysis on the left, you click OP. Go down. OP. Yeah, this one. Up. Yeah. The thing OP above the variable.
Under the pen down menu.
Okay. You go to plot axis. Go move your cursor up. Yeah, this one operating point. You double click instance. It will bring you back to the schematic. And then you click either one. You click the tail and mouse. Yeah, click. Child instance. You put M1. Parameter name. You select region. Scroll down. Yeah, you can see OP. Yeah, the expression. Yeah, here. And then you click add to output. Yes, add. Yeah. What is I7? Oh, it's okay. I7. Name you can put empty. Follow your naming, how you want to tabulate the data, and then you can click plot. Not this one. And there's a plot at the bottom right. Go down.
The whole window is beside clear. You go down to there's 2 buttons to press.
Yeah. Okay, plot. You open the result viewer. The tab beside. Yeah, this one. Yeah, this one. No, the tab, the window tab beside the primary just now. Yeah. 0.5, 500 milli is linear, so it shows across PVT. This transistor is not saturated. You can just copy the pattern. Go to primary. Yeah, you can follow that expression. Yeah, this one. Yeah, 1 is saturated, 0.5 is linear, 0.05 is subthreshold, 0 is cut off. Yeah. Yeah. Yeah, you check to make the op-amp function. VD set 1.61. Anything else you want to ask? Yes. And also transient. But at first you try with DC. Nothing from me. Okay. Yeah.
I'm still thinking a bit lah. Maybe Mr. Daniel, just to get some insights from you lah.
Okay.
Usually when you see that previously when we test the whole circuit, we use a common mode of, I think we supply a steady state of DC voltage lah. We supply, I think, VDD over 2 to both gates of the op amp lah. And then we managed to get all op amp in, I mean all the MOSFET in saturation, right?
Okay.
And then when you start to run the DC simulation, maybe can you give us a brief summary lah? What do you actually do in the DC simulation so that we know actually where might be the problem because the moment we run the DC simulation, some of the MOSFET actually went to cut off which we did not expect at all
Can you go to the test bench schematic? Previously, do you guys use the current load 50 milliampere? Yes. Previously, do you guys test with the IDC 50 milliampere at the output at the V out there is beside the capacitor. Because this op amp needs to drive like 50 milliampere load. If it able means that the op amp able to supply like 50 milliampere up to able to supply. Previously, do you guys add this current load or just run the op amp? You try to remove the wire connected to the current source. Remove this and then run the simulation again. Just click the net and delete. Click the middle.
Click the wire.
Click the middle. Now it's okay. Now also okay. You save and then run the simulation again. Yeah, now looks fine. V out. Yeah, now is tracking, right?
So this means that the op-amp was not able to support that much current. That's why the other MOSFET they went to cut off.
Yeah. The output side, the current to yeah. I need to ensure the second stage can able to supply this much current.
Oh, so usually the problem lies at the second stage lah.
Yeah. You can drag V out, overlap with VIP. You drag it. You just press and yes. You're able to supply 50 milliampere.
So in this case, it's actually the ability for the op-amp to source current, right? Which means that it will be the PMOS problem.
Yes. And right. Yes.
Okay. Usually for PMOS, what is the largest width that you can have?
I
in
think
industry?
this one actually I I haven't designed. Can you go back? Go inside the symbol. This one I might need to confirm with Mr. Yadi. Can you go? Can you click the second stage, PMOS? Oh, just close this window. I think this size can. You click.
I think this one is M3 or not M7.
You
Because
escape.
you are looking at M7, right?
You
Zoom in a
click.
bit.
You click escape. Cancel. Escape. And then click. You can adjust with separate M device and get per device at the above, below the length. This one, the maximum, I need to confirm first. But I think in this case, larger the better.
Okay. So any other questions? Yeah, go back and work on it first. Remember to put in the enable. In this original one, I don't think you put in. I think the previous, the V2 version, right? You got put in the enable. got test it out lah. Yeah, maybe start without the enable first, or once you get the op-amp to work without enable, then afterwards you get in enable lah. Okay, then should we call it a day?
Okay. If you guys have any question, you can just WhatsApp me.
Yeah, all right. Thank you, Mr. Daniel, for spending the time with us. Yeah.
Thank you.
Thank you, Mr. Lai.
Thank you very much.
Okay, bye.
Make sure you all go back and work proactively. Yeah. Get things done as quick as possible lah, because the next review session is next week already. Yeah. Okay.
Yes, thank you, sir.
Okay, all the best. Okay, bye-bye.